Okay, physics. I want to get into springs and Hooke's law and describe those just in terms of forces for right now. We're going to return to springs and look at them in a couple of different cases when we get to energy and then oscillations as well. But right now we're just dealing with the forces that are involved with springs, and the corollary to that, of course, is whenever we deal with forces, we're also dealing with acceleration. So let's take a look at this. So curious things about springs. So here's a spring. This is a PhET simulation. Really handy to get your head around some of these things. So notice that when it's at this equilibrium point, so when it's at a relaxed state, that there's no force that's applied. And as I pull the spring, it takes some force to pull it, right? So not surprisingly. The thing that's different about springs, though, is that the further I pull it, the more force it takes, right? So I've pulled it a little bit of distance, and that takes 29 newtons to hold it there. If I stretch it further, right now it's taking me 88 newtons to hold it there. So this is an example of a non-constant force, and for physics 1, this is pretty much the most common and only example that we'll come across of non-constant force. For physics C, well, yeah, get used to it. So this is a non-constant force. So we want to be careful about this. And so we'll have a way of describing this. A couple important things. So one, we're going to describe the characteristics of the spring with the spring constant. And the spring constant is going to tell me how much force it takes to stretch it 1 meter. Right? Even if I have a short spring, I can scale it, right? So this spring constant for this one tells me it's going to take me 200 newtons to stretch it 1 meter. So this is a way of describing a spring, and every spring is going to be a little bit different, right? So these are the things that we care about. Is going to be the force that it takes to stretch it, the spring constant itself, and then essentially how far we stretch it. So this is what Hooke's law does. It provides this relationship. And if we were in class, we'd be able to do a nice lab and be able to try a bunch of springs and come up with this mathematically. But let me just tell you about it now instead. So Hooke's law. Hooke's law says there's a relationship. Where does it go? Okay. Hooke's law says very specifically says there's a relationship. So my force on the spring is going to be equal to some spring constant. I'm going to call this K times the distance it's been stretched, right? So this is my spring constant. And this is always going to be a positive value, right? Because we're going to say, well, I'm going to stretch it, and the units are going to be newtons per meter. And the way I think about this is, like I said, so is how many newtons does it take to stretch it out to 1 meter? So each spring is going to have its own individual spring constant. So it's a constant. We use the letter K, which, yeah, we use for other things as well. But it's only constant for that individual spring, right? So you don't know what it is for another spring unless you determine it experimentally. X is the distance that something is stretched. So notice that as I stretch, the further I stretch it, then I'm going to have a larger distance, and the force it takes to hold it there is going to be higher. So importantly, though, this is the force that the spring's exerting. So notice when I stretch the spring of that simulation, I pulled the string out in one direction by applying a force, an external force in that direction. Here we're talking about the force the spring is applying, and the spring is applying a force in the opposite direction. So we're going to put a negative sign on there to indicate this, right? So this is the force the spring is applying. And we can show what this looks like on this little simulation, right? So if I drag this out to here, so now I'm spending 100 newtons on this. So this is the force that I'm applying, or this is my external force. What we calculate is the force that's coming from the spring. And like any contact point, those two forces are going to be balanced. So the force that I apply is going to be equal and opposite to the force that the spring is providing in the opposite direction, right? So what we really care about and what we calculate is not the applied force. What we calculate is what's that force coming from the spring. Right? So this is the direction of the force. But notice that when I get on the other side of equilibrium, the direction of the force changes. Right? So to figure out the direction, you either need to know which side of equilibrium you're on, or you can say is always going to be back towards the equilibrium point. So notice that my force is always directed back towards the equilibrium point. Okay, last thing to mention about this is we can connect this to Newton's second law, right? So acceleration is going to be the sum of the forces over the mass. So if I have a mass on the end of a spring, which we're going to do it a bunch, so the spring force is going to be equal to mass times acceleration. So notice that mass is a scalar, it's just a value, so it's a number. Force is a vector and acceleration is a vector. So whatever direction the force is, that must also be the direction of acceleration. So, think about this. So back in the simulation here, so my force is back towards the equilibrium point, and acceleration must also be back towards that same point. As I go on the other side, my force again is headed back towards the equilibrium point. My acceleration must also be back towards the equilibrium point. Okay, and of course we could graph this, right? So force equals negative kx. This is a Hooke's law, so y equals mx is my way I'm going to think about this. So I'm going to plot force on my y-axis and displacement on my x-axis. And I will find with increasing force, increasing displacement. So notice now this is the force that I applied to get it. So it's going to be opposite direction. So I can get a value of k from the slope of this. And this is Hooke's law, so this is how we determine. So we apply an external force. And a lot of times we'll do this from a, we can hang a mass and see how far it stretches from the equilibrium point. Put a different mass on there. So here the force, the external force we're applying is mg, and the displacement we can measure from the equilibrium point, and with that we should be able to figure out what the spring constant is. And if we were in the lab, we'd be able to do this real easily and it'd be fun, but we're not, so sorry. Talk to you soon. Bye.